watch an Airbus A380 takeoff. That massive fuselage longer than two blue whales slowly, almost reluctantly lifts from the runway. Four engines, each producing 70,000 pounds of thrust, roar at maximum power. But something's wrong with this picture. While a Boeing 777 rockets upward at 3,000 feet per minute, the A380 crawls skyward at half that rate. It's not broken. It's not underpowered. This is by design. You're looking at the heaviest passenger aircraft ever built, struggling against a fundamental law of physics that no amount of engineering can overcome. An aircraft so massive that pilots need special procedures just to coax it to cruising altitude, so compromised by its own size that it literally cannot climb as high as planes, half its weight. This isn't just about slow climb rates, it's about an engineering trade-off so severe it helped kill the super jumbo era. From wings that should have been 10 meters longer to engines that seem powerful, until you do the math. This is the untold story of why the world's largest passenger plane can't get high. If you love aviation and want to learn more about the incredible engineering decisions that shape the aircraft we fly on, hit that subscribe button. Because what you're about to discover will change how you see every A380 struggling into the sky. The numbers that don't add up, let me hit you with a number that makes pilots wins. 0.23. That's the A380 thrust-to-weight ratio for context. A 747 manages 0.29, a 777, 0.30 or better. That means for every pound of aircraft, the A380 has 23% less power pushing it skyward than its competitors. Think about that. You've got four massive engines, 300,000 pounds of total thrust, and it's still not enough. Why? Because this beast weighs 1.26 million pounds at maximum takeoff. That's 575,000 kilograms, the weight of 100 elephants. Here's what that means in the real world. Initial climb rate 1,500 feet per minute, maybe on a good day with a tailwind. Compare that to a 787 or a 350 hitting 3,000 feet per minute without breaking a sweat. But wait, it gets worse. The service ceiling, officially 43,000 feet, sounds impressive until you realize the A380 can actually get there. When it's heavy at maximum weight, you're looking at 33,000 feet. That's it. That's your ceiling for the first several hours of flight. Meanwhile, that 777 next to you already cruising at 41,000 feet, burning less fuel and thinner air while you're stuck down in the weather. And turbulence. The wing loading tells the rest of the story. 680 kilograms per square meter, among the highest in commercial aviation. Every square foot of wing is supporting 1,400 pounds. It's like asking a marathon runner to carry a refrigerator. These aren't just numbers on a spec sheet, they're the difference between making your flight plan and burning thousands of gallons of extra fuel, between smooth air and turbulence, between profit and loss. The 80-meter box that ruined everything. Here's the decision that doomed the A380's climb performance before the first rivet was installed. Back in the design phase, Airbus faced a choice: build the aerodynamically perfect wing 90 meters across, optimize for efficiency, or constrain it to fit existing airports. They chose the airports. The result? A 79.75-meter wingspan, just under the 80-meter limit that keeps the A380 in the same airport category as a 747 seems reasonable. Right, wrong. That 10-meter compromise cost everything. The aspect ratio, the relationship between wingspan and wing area, dropped to 7.53 modern efficient wings. They're pushing 9 or higher. This seemingly small number translates to 10% more drag every second of every flight. Here's what Airbus never advertised. Those beautiful wings are fundamentally wrong for the airplane they're attached to. Too small for the weight, too short for the fuselage. A band-aid on a physics problem, Virginia Tech ran the numbers. The induced drag coefficient, 0.09564. For comparison, an optimally designed wing would be 15 to 20% lower when you're trying to haul 575 tons into the sky. That extra drag is like climbing stairs with ankle weight. But here's the kicker. Even if airports could handle bigger wings, the A380 would still struggle because of something called scaling laws double in aircraft size, and its volume grows 8 times, but wing area only 4 times. Weight grows faster than lift. It's mathematics. And mathematics doesn't care about your business model. The ground effect makes this worse. During takeoff, when the A380 is within 40 meters of the ground, about half its wingspan, it gets a 40% drag reduction. Sounds great until you realize what happens when you leave ground effect. That drag comes back hard, like hitting an invisible wall at 200 feet. Watch an A380 take off closely. See that moment where the climb rate flattens? That's physics collecting its bill. Why? Pilots have a love-hate relationship. Talk to A380 pilots, and you'll hear the same phrase. Step climb. Unlike other aircraft that can climb straight to optimal altitude, the A380 plays hopscotch with the sky. Start at 33,000 feet, burn off some fuel, request 35,000, burn more, request 37,000. Maybe if you're lucky and light enough, you'll see 41,000 feet before descent. Each step requires a TC approval. Each request adds to controller workload. In busy airspace, you might get denied, stuck at a suboptimal altitude, burning extra fuel because your airplane is too heavy to climb. Emirates pilots flying the world's largest A380 fleet have special procedures. Below 10,000 feet, maintain 250 knots with whatever vertical speed you can manage above 10,000. Accelerate to 320 knots, but don't expect miracles. The plane will climb when it wants to climb. The training manual puts it diplomatically. Special attention required due to the plane size. Transol. This thing climbs like a truck. Here's what passengers never know. When pilots request super heavy designation from a TC, controllers immediately adjust expectations, longer climb clearances, wider separation, special handling. The A380 doesn't just fly through airspace, it disrupts it. Flying 2,000 feet below optimal altitude, that's 600 kilograms of extra fuel per hour. Over a 14-hour flight, you've burned an extra 8,400 kilograms at current fuel prices. That's $10,000 down the drain. Per flight, because your plane can't climb, the descent is equally painful. While a 777 can drop at 1,500 feet per minute, the A380 manages 1,000 feet per minute. Maybe pilots start their descent 30 minutes early. Half an hour of extra flight time because going down is almost as hard as going up, weather avoidance. Forget it. That thunderstorm at your altitude, other planes climb over it. The A380 goes around it or through it. Your choice. The competition that exposed the truth. Put the A380 next to its rivals and the problem becomes embarrassing. Boeing 777-300ER, 2,500 feet per minute. Initial climb, thrust-to-weight ratio, 0.30. Time to buoy, 3:10:23 minutes. Airbus, A350-1000, 3,000 feet per minute climb rate. Latest generation engines can reach flight level 410, while the A380 is still struggling through flight level 350. Even the ancient 747-400 embarrasses. Its successor, higher thrust-to-weight ratio, better climb performance, and it's a design from the 1980s. Here's the stat that killed the A380 operational flexibility. A 777 can change altitude for weather or traffic optimization in minutes. The A380 needs to plan altitude changes like military operations, request early climb, slowly hope for approval. Modern twins don't just climb faster, they climb smarter. Variable camera wings, advanced flight management systems, engines that maintain efficiency across wider altitude ranges. The A380 has 4 engines designed for crews struggling to provide climb power when needed. Time to altitude tells a story. A 777-300ER needs 23 minutes to reach FL 310 and a 380 at 11 minutes. That's 11 extra minutes of fuel burn at suboptimal altitude. 140 kilometers of extra distance traveled just to reach cruise height. Multiply that by thousands of flights, and you understand why airlines chose twins. The 787 Dreamliner really twisted the knife half the size, twice the climb rate, better fuel economy, same range. Why struggle with a super heavy when a regular heavy does the job better? How Emirates made it work and why nobody else could. Here's the miracle. Emirates operates 123 A380s profitably. How scale when you have 100-plus aircraft? The specialized training procedures and infrastructure become economical. As Tim Clark said, if you've got a sub-fleet of 10, it's a bloody nightmare, but if you've got 100 of them, it's a bit different. Emirates built their entire operation around the A380's limitation, special climb procedures, dedicated flight planning teams, routes optimized for the aircraft's performance envelope. They turned weaknesses into operational standards, but even Emirates can't overcome physics. Their pilots still request step climbs. Their aircraft still burn extra fuel at suboptimal altitude. They just spread those costs across enough flights to make the math work for everyone else. Disaster. British Airways, Air France, Lufthansa, they all discovered the same truth without scale. The A380's climb limitations multiply every other operational challenge. Small fleets mean higher training costs per pilot. Fewer routes mean less flexibility to accommodate performance limitations. Singapore Airlines, despite their premium-heavy route, couldn't justify the operational complexity. When your fleet of 19 aircraft requires specialized everything from pilots to procedures, the economics collapse, the fix that never came. Airbus knew, they always knew, the proposed A380 Plus would have extended the wingspan to 84 meters. Just 4 meters, but enough to reduce drag by 4%, new winglets, optimized wing twist, marginal gains that might have helped, but airports said no. That 80-meter box wasn't negotiable. Break it. And suddenly the A380 meets new gates, new taxiways, new everything. The infrastructure investment would dwarf any efficiency gains, engine improvements. The Rolls-Royce Trent 900 and Engine Alliance GP 7200 received updates, but thrust wasn't really the problem. The problem was weights and wings, and the fundamental reality that making planes bigger doesn't make them better. The fly-by-wire system got smarter. Optimized climb profiles, automated step climb management software, band-aids on hardware problems. You can optimize all you want. You can't code your way around physics. Carbon fiber wings were considered, might have saved weight, might have improved the thrust-to-weight ratio by a few percentage points, but the development cost billions for an aircraft. Already struggling to find buyers, dead on arrival. The lesson hidden in the climb rate. The A380's altitude struggle isn't just about climb rates. It's about what happens when you optimize for the wrong thing. Airbus optimized for passenger capacity, 850 people in maximum configuration. The hub and spoke model demanded it. Pack them in, fly them between mega hubs, distribute them on smaller planes. The theory was perfect. The reality, airlines discovered that two 787s offered more flexibility than one A380, different departure times, multiple route options. And yes, better climb performance that translated to fuel savings and operational efficiency. The A380 proved that bigger isn't always better. That airport compatibility matters more than aerodynamic perfection. That operational flexibility trumps maximum capacity. Every struggling climb reinforced these lessons. Physics doesn't negotiate. You can have the most advanced flight control systems, the best pilots, the perfect procedures, but when your thrust-to-weight ratio is 0.23, when your wings are fundamentally compromised, when your weight exceeds what your design can efficiently handle, you get what the A380 delivered: the slowest climbing wide body in the sky. Watch an A380 struggle skyward, and you're watching the death of the super jumbo era. Not in a single dramatic moment, but in thousands of incremental inefficiencies. Every delayed climb, every step, climb request, every extra gallon of fuel burned at suboptimal altitude. The market delivered its verdict. 251 orders total. Boeing sold that many 777s. In 2 good years, the A380 program lost an estimated $25 billion. Not because it was a bad plane, but because it was the wrong plane optimized for a world that no longer existed. The irony, the A380 is beloved by passengers. Quiet, spacious, smooth, that massive weight that kills climb performance also dampens turbulence. Those compromised wings still deliver a magic carpet ride. But airlines don't buy planes for passenger comfort. They buy them to make money. And every foot of altitude the A380 couldn't reach was profit. It couldn't generate the A380 will keep flying for years. Emirates will squeeze every dollar from their fleet, but watch them climb slowly, reluctantly, step by painful step, and remember, you're watching the last of their kind. Future planes will be smaller, more efficient, and yes, much better at gaining altitude. Physics 1. Physics always win. What do you think is the A380 passenger experience worth its operational limitations? Or did Airbus build the wrong plane for the modern world? Drop your thoughts in the comments below, and remember, if you want to discover more incredible stories about aviation's biggest engineering challenges, that subscribe button is right there.